So thanks for the introduction, Alex. So good afternoon from very sunny Malta at the moment. My name is Bugeja, and today I'll be presenting my talk on Playfully Learning by Imitation. As a way of introduction, I'm currently a PhD candidate at the University of Malta, starting what is hopefully my final year in my PhD studies. My research work is mostly based on machine learning and computer vision, but like most of you here, I imagine, I started my computing studies because of my interest in the games industry and later on in game development. So why use AI in games? AI in games is used extensively in a number of different areas. This ranges from use in game engines such as techniques that are used to optimize the physics as well as the rendering of game engines to other areas that deal with game content. For example, procedure level generation, which are a set of techniques that are used to generate game levels in game worlds. Other aspects include agents that solve puzzle games. These techniques also go very well with procedure generations, as these agents can be used to verify if the level that you generated through AI is actually solvable or not. Finally, AI is also used to develop agents that play a game by competing with the player, playing against the player, or together with the player. And this brings me to one of the most popular areas in AI that has to do with games, although it's also used extensively in robotics, called reinforcement learning. And reinforcement learning is an approach where a model, referred to as an agent, learns by exploring an environment. This is unlike other machine learning algorithms that usually learn by finding patterns in a set of features and learn how to associate that pattern with some label. For example, learn how to distinguish the difference between a cat and a dog. The action that the agent can take are pre-established, and the agent learns how to apply those actions in order to solve some goal. So the goal being, in the case of games, how to play the game. This can be something as simple as learning how to navigate through a room, so think about something like Roomba, or playing a real-time strategic game or driving a car or an airplane. And we have seen currently there is a lot of work in self-driving cars that use reinforcement learning as well as a model that I'll be talking about later on in the talk. So reinforcement learning has a number of features, including the ability to learn what action to take through trial and error, learn how to sacrifice short-term reward to gain a higher long-term reward later, the difference between exploiting a short-term goal or exploring to maybe find something better later on. This approach is very similar to how we learn as humans to take certain actions. So quite recently, I was blessed with a baby girl, and over the last couple of months, I have seen her develop new skills. At our age, we take most of the things that we are able to do for granted. But for me, it was very fascinating to see how she managed to learn something like rolling through trial and error. So at this moment, I basically have a small reinforcement learning agent at home that it is a fun way to see how AI has been translated from the way humans learn to actually how to teach machines. One of the biggest problems with working with reinforcement learning is, like in most other machine learning areas, is the curse of dimensionality. So the more complex your environment, the more training is needed for the agent to explore, or sometimes even not explore, enough to manage to take the optimal decisions when playing games. In 2013, Min et al., working with DeepMinds, developed a deep reinforcement learning approach that added convolutional neural networks to a traditional Q-learning agent. So basically, the agent now takes raw input pixels as an input and outputs an optimized value function. So for those of you who maybe do not know what a convolutional neural network is, this is simply a subset of neural network techniques that instead of learning through handcrafted features, usually in computer vision, you'd get an image, you'd use feature extraction techniques to extract specific patterns from the images, and then use those features to teach a neural network how to distinguish, for example, between different objects. But with convolutional neural network, we do not have to anymore do this handcrafting of features process before we actually start training the model, because the network will do this for us. So it will basically feed it a lot of images, and with enough training data, it will be able to find features on its own that distinguish between different objects in your images. So this state-of-the-art approach, when I'm talking back now on deep reinforcement learning, was applied to a number of Atari games and successfully managed to outperform not only previous implementation, but also a number of human experts in playing the game. So, for example, if you see in the video over here, this is a breakout. So at this stage, the agent is trying to learn the game. So obviously, certain times it loses, but after just 120 minutes of training, through reinforcement, deep reinforcement learning, deep Q learning in this case, it plays the game like an expert. Obviously, we are talking about a very simple game in terms of what actions it can take. So these are some examples which you've already seen in some of the other talks. So with deep reinforcement learning, deep minds especially continue to develop this key aspect further. And what happened is an increase in the number of deep reinforcement learning methods that increasingly solved more complex games and was even able to defeat top human players in StarCraft and Go. Google has released a number of AlphaGo versions, with the final version, AlphaGo 0, managing to beat the previous versions of AlphaGo as well as human experts. What is interesting about this is the fact that the previous models also managed to beat these human experts. So Go masters are now looking at the way AlphaGo 0 plays the game in order to come up with new strategies on how they themselves should play it. So basically now it's kind of the reverse. Humans are now learning from the machine. So with games such as Go, the agent is not performing actions that might be very easy for a human to know whether they are playing against a machine or a human. On the other hand, if you consider something like a first-person shooter, the way the agent walks, runs, or aims already give a pretty good indication of how believable that agent is at imitating a human playing. Which brings us to a possible problem, where players want to engage with games that are as natural playing as possible. On the other hand, if a player plays against the same agent, the probability is that the agent is slow to adapt to the player's play, and with enough experience, the player is able to predict the action a player takes and win easily. So the question is, can we create agents that play games by imitating players playing? Which brings me to my next set of models, techniques, which are called imitation learning. So imitation learning, sometimes referred to as apprenticeship learning, you might find it also as reverse reinforcement learning or behavior cloning, are a set of techniques and models that learn through observation. So unlike reinforcement learning, these agents observe someone else performing a task and learn how to associate the actions taken by that person or agent with some goal. And with enough observations or demonstrations, the agent learns to optimize for a given task. The effectiveness of the agent is entirely dependent on the data and ultimately on the actions taken by the human. So if this is applied to games, the better the player, the better the agent. Going back to reinforcement learning, I previously mentioned how I observed my daughter learning by exploring the actions she can take. But recently, I have also noticed a new pattern in the way she learns. Basically, she is now imitating sounds and actions that we do at home. So, as with most AI approaches today, these models are always inspired by human behavior. An interesting point is that imitation learning acts more like supervised or self-supervised machine learning techniques. So the difference here is that previously, when it came to reinforcement learning, I was mentioning a set of models, set of techniques that learn by exploration, so you do not need any preliminary data. As I said before, imitation learning uses observations. So it is more similar to something like a neural network because you are feeding it the demonstrations, the actions, the data. It is looking at that data, and the label in this case, instead of being an object like a cat or a dog, in this case, it's an action. It's what it should do. And as an input, it will take either the actions themselves or in some models, even the pixels. One thing to keep in mind is that for a virtual game agent to be believable, the player must not notice that he is playing against a machine. So a quote that I found is that believability of a virtual agent is associated with giving the illusion of being controlled by a human. So imitation learning is not a new area. In fact, there is a lot of research in this area with focus on applications in robotics. But there is also some research in games. The reason why it has recently become more popular is, like with a lot of different machine learning techniques, the rapid improvement of processing technology, which has allowed us to train models faster, paving the way for faster research and general optimization of networks and generation of new ideas, where before it would take you 7 or 8 days just to train a model, a simple model on some features. Today, you can train that model in half an hour or 1 hour. That means that in one day, I can train 8 different implementations of the same model and find the best way forward. There's also a lot of potential for using imitation learning in esports. So how does this affect esports? So in esports, competitive players undergo a lot of training to compete. A possibly useful use of imitation learning is to train models on specific player playstyles by observing these players playing. Thus, in this case, let's say you have someone who is training to play a particular game, let's say, for example, FIFA. And in this particular competition, he knows that he's going to face a number of competitors. Then by using imitation learning, you can train that model on observations of plays from these particular players. And then through that trained agent, the actual human player can now train against them and gain a bit of a competitive advantage in when he actually faces the real human. And the same process can be applied to a number of different scenarios. For example, training an agent on multiple players. And the better the players, you can now separate categories between very good players or average players or starting out beginner players, thus creating more kind of a process where players can play against these agents that act like a human, therefore slowly improving your own skill set. And finally, training an agent to play exactly the way you play in order to find problems with your playstyle. So, in conclusion, we have taken a look at some of the traditional AI techniques used to train agents to play games. We have defined the difference between reinforcement learning and imitation learning techniques, and explored how imitation learning can be used in games, and saw how these techniques can be potentially used in esports. Thanks for listening, and any questions?